Okay, so this is about neural networks or artificial neural network. So how many of you do not have any idea about neural networks? Zero idea. Can you guys respond on chat with +1 whatever? Okay, absolutely zero idea. Okay, that's good. Okay, fine, I understand. So since there is a separate uh, separate course on deep learning, here the plan is to give a very brief basic overview of neural network. I will start with normal artificial neural network, perceptron, multilayer perceptron, etc. And then I will go deep into uh, convolutional network, recurrent network, if the time permits. Of course, I mean, we'll try to cover these two, at least these two concepts, and then we'll discuss, if again the time permits, we'll briefly discuss about LSTM, GRU, slightly specialized neural networks. Okay, and I assume that so I will assume that you guys do not absolutely have no ideas about deep learning. So I'll start from the very basics. I'm pretty sure some of you have possibly ideas about the basics, so you may want to skip those part, but since this is fundamental machine learning course, I thought I should start from the scratch. Okay, so I mean, if you remember the history of deep learning, neural networks, forget about deep learning. We'll not use the term deep learning in this chapter, okay? Because the kind of network that we are going to discuss here would not be that deep. So we'll use the terminology called neural network, okay? So if you look at the history of neural network, way back 1980s, 1985, people proposed 1970, 1975, around that time, this concept of perceptron was proposed. We'll discuss this thing, perceptron, today. And then, and basically the idea was to mimic how a human brain operates, right? When we get signals from environment, different situations, heat, temperature, cold, etc., how our nervous system operates. And basically that was an attempt, very preliminary attempt to mimic nervous system, human nervous system. Then perceptron was proposed. Perceptron turned out to be effective in some cases, but then people started, because there were two different schools of thoughts. One was more into statistical machine learning, and other is more into neural machine learning. Statistical machine learning, people looked at regression, SVM, those kind of stuffs, where neural networks people looked at in different angles. And there is, since there are two schools of thoughts, there is always a kind of war between them. And statistician, they tried to dominate at that time, and they showed some of the drawbacks of perceptron. So deep learning, I mean, the research on deep learning got halted for few years, again 1988, 1990s, around that time. Hilton, and then Jan LeCun and their teams, they started working on a simple network, simple neural network, slightly deep. Looked at multilayer perceptron. Multilayer perceptron turned out to be very effective in some cases where we have nonlinearity in the data set, right? And then we know the rest of the histories. So so today we start with I mean, the ideas, the anecdote, why it is called neural network. I'm pretty sure you guys know that. I mean, I'm not very good in biology, but if you remember your 11th standard, 12th standard biological science, we have seen that we have millions of neurons present in our body. And the way it operates, each of them operates is that they have this these spikes called dendroids, right? So dendrites, I guess. I do not remember the exact term, but I think dendrites. And this spokes, they basically get sense from environment, for example, heat and other kind of sense, and then then this senses this sensor pass through the the actual cell. So this is the cell, right? And then it activates the the neuron. Okay, so it's called nuclear. Okay, and then if say this neuron is not responsible for certain kind of signals, it would then pass that signal to other neuron, and all these neurons are interlinked. Okay, there is another neuron, so for example like this, and it is connected to these are the dendroid and these are called axon, right? So all these the signals look like an electric signal, and then it gets passed through other neurons for further processing. So essentially, the idea is that you get signals from outside environment, right? We call them inputs, okay? And once you get the inputs, I mean, if this neuron is responsible for those types of inputs, the nuclear gets activated. Okay, if it is not responsible, those inputs are passed through the axons, and they further activate the other neurons. Okay, so this is the overall idea of and if you look at our nervous systems, there are two zones. One is called central nervous system, and so we have central nervous systems and peripheral nervous systems. So peripheral nervous system is responsible to receive signals from outside environment, and central nervous system basically acts to those signals. Okay, so the idea of neural network is basically is to mimic the way our nervous system works, right? In this case also we have different input signals. Okay, so inputs are there, and those inputs are basically passed. So you can think of these as inputs x1, x2, x3, x4, say, and these inputs are then fed to the the main cell, right? The main cell body, right? Which we call as a cell, right? This is a cell, and if these inputs are responsible to activate them, then the cell gets activated. And here activation means we basically invoke an activation function f. Okay, and depending upon that, the output of the function, I mean the of course the input, the function will react accordingly, and then it would tell us whether we should be afraid, or we should be jealous, or we should run away from the situation, etc., etc. Okay, so we have certain output. So this is a block diagram of a single neuron. Okay, and these blocks, so this particular block is called neuron, right? Single neuron with 4 inputs, right? So so if you look at the first successful study with neural network as an application, right? There is a tool, not a tool. There is an experiment. The name of the experiment was Alvin. Okay, so it was designed by one of the faculties in CMU. Okay, so this Alvin, this was a kind of automatic vehicle driving system, right? So you have this neural network in your, I mean, assume that it is already, it is deployed to the steering of the wheel, I mean steering of your car, and then you get images. You have some camera deployed in front of the car, and you are getting images of the roads, whatever obstacles you have, right? And depending upon that images, you decide whether you need to move right or move left, or you need to increase your speed or decrease your speed, or need to stop, and so on. So this was a first, I would not say successful, but it was the first published work, right? Where it was showed that a simple 3-layer perceptron, we'll discuss, right? 3-layer perceptron can achieve a significant result in this kind of autonomous vehicle driving, right, at a normal speed on public highways. So and after that, a lot of things, lot of applications underwent in different domains, mostly biology and biological domain, where you have images of multiple parts, different parts of human body, and they try to scan things and then basically classify things in different ways, right? This Alvin method, in this case, so you have this image, a pixel, right? uh, I think is that was 32 30 cross 32 kind of input image, and you had some hidden representation, hidden layer, and then you have classify, I mean, and you have that output. Okay, it's a fully connected, and the output was, say, shift left or right or move ahead. 3 outputs, something like this. So let's try to understand why, I mean, where neural network methods, techniques are useful. Okay, the places, the cases where we think of applying neural network, not traditional statistical methods. Okay, so we have, say, instances represented by attribute value pair. Okay, so you have training sets and training set, each instance is represented by a set of features and its corresponding values. Then you can apply neural network when the target function, your target function may be a discrete value, right, or real value.
Sir, could you please
Or
repeat the first one?
yeah, I mean, the first one says that all the instances, this is very general, and all the instances should look like a tuple of attributes and values. You have attributes and the corresponding values.
Okay, okay.
Real value, so the target function can be real value, discrete values, or it's a vector, right? It's quite flexible in that case. Third case would be if your training set has error. Okay, so if a training set has error, then also you can use neural network, because it turned out that they are not that sensitive to error. I mean, if you have small amount of error, that is not resilient to that is resilient to error. Okay, it's not that sensitive to error. Okay, when you have the possibilities to accept long training time. Okay, because usually neural network methods take a lot of time while training. Okay, if you have that situation where you want to accept such long delay, then that is okay. In that case, you can use neural network, or say when you need, I mean, when you have the possibilities to evaluate, fast evaluation of learned target function, right? In that case, you can use neural network, because whatever you learn, you can quickly evaluate it, right? And say for example, in case of Alvin, right, it applies neural network several times per second to continuously update its steering command as the vehicle drives forward. Okay, so because you have a very simple evaluation method, you just see the ground truth and quickly evaluate. You do not need extrinsic evaluation or evaluation from third party, right? So in that case, you can use neural network. And if you have that flexibility not to explain the underlying principle, you can still use you can use neural network in that case, because it's very difficult to explain what is happening inside. Okay, as you know, these days explainability is a major concern in deep learning. So but if you have the flexibility that you do not need to explain what is happening, why your result looks like this, then you can use neural network. Okay, so these are the cases, these are the appropriate problems where you can use artificial neural network. Okay, so the first artificial neural network, or the first attempt to mimic nervous system, was perceptron. So perceptrons. So the idea is very simple. In the preliminary level, it may look like a logistic regression, a kind of a linear regression. Okay, so it looks like this. You have xn, x1, x2, dot 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 xn, n number of inputs, right? And these inputs are fed to a neuron. Okay, and along with when they are fed, they are multiplied with some weights. We all know this. So w1, w2, dot dot wn, right? What this neuron does, this neuron, basically the task of this neuron is basically to first task is to take a sum of all the inputs. So summation of xi wi, right? I equals to 1 to n, right? So along with this, remember there is another input which we call as bias. Okay, so we call it x0. We have already seen in case of linear regression, logistic regression, x0 is 1. Okay, and it has certain weight. We need to, so this weight is also a parameter, right? So we can simply write as x1 w1 plus x2 w2 plus dot 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 plus xn wn plus w0, okay, which is the bias. Just to make this thing everything within the sum, we consider another thing which is x0, another input x0, whose value is always 1. Therefore we can write this as I equals to 0 to n xi times wi, right? So far this exactly looks like a linear regression, right? Then what is happening? So along with that, so there is an additional function. Okay, and we call this additional function as activation function later, but assume that for the time being this is just an additional function which takes sum of xi wi as input and returns this kind of value, right? Return 1 or -1 if sum of xi wi is greater than 0 otherwise. Okay, so the output of this perceptron is 1 or -1. Okay, now so you see what I mean. So output is 1 or -1, and you have certain inputs. So your task would be to tune all the parameters W0 to Wn in such a way that it would satisfy the ground truth that we have. Okay, so now if you think of this one, so summation w1 x1 w2 x2 dot 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 wn xn plus w0, this is the actual function, right? And if this is greater than 0, then your output is +1, otherwise -1. So essentially this part is there, this part from x1 to xn, this part comes from outside world, because x1 x2 xn, these you do not have control on, right? So they are coming from outside world. So if this part, if some of this part is is what is think of two portion, you have this one and you have w0. Okay, you basically add this part with w0, and you check whether it is greater than 0 or less than 0. Yes,
इतना अंधेरा तो कर रखा है रूम में,
सही लग रहा है, कुछ नहीं हो रहा है।
what happened? Please mute yourself. Okay, so this is the task. Now the good part, so how do we write? We write this as O of, this is not A, sorry, it's O, sorry, O of. So O x is the input, and SGN sign, essentially sign, because you are checking whether it greater than 0 or less than 0. Less than 0 means negative, and greater than 0 means positive. So sign of W matrix and X matrix. Okay, and how do we define the sign? Sign of Y is 1 if Y greater than 0, or -1 if Y less than 0. Right? So perceptron is very successful in in separating those points which are linearly separable, right? For example, say you have these points plus minus minus, they can be easily separable, right? So therefore it turned out that it is successful to mimic functions like AND or, right? Because AND truth table x1 x2, right? 0 0 0 0 1 0 1 1 0 0 and 1 1 1, right? So if you plot these points in a 2D space, so 0 0 means this point, right? So 0 means -1, so -1 -1 -1 +1, this is the output, right? Ground truth. So -1 0 0 0 1 means 0 1, this point, this is also -1, right? 1 0 means this point, this is also -1, and 1 1 means this point, this is +1, right? So so these points can be linearly separable. So if you train your perceptron to mimic this AND function, right, you see that W0 value would be -0.8, and W1 and W2, they would be 0.5, right? If you train the perceptron for OR function, right, which looks like, let's again plot it, 0 0 minus 0 1 0 1 plus 1 0 plus 1 1 plus, you can also separate them linearly, right? If you train the models, you see that W0 would be -0.3, and W1 W2 would be 0.5. Now think about it, with same W1 W2, you just change the weight of the bias term. and you get two different outputs, right? In fact, it turned out that it can handle all m of n function. What is m of n function? So m of n functions are those where at least m of the n input are true, means plus 1. Okay, so I mean, so m of n function, this is a generic type, right? Where and or, they are two specific cases. In case of and, right? In case of ands, m equals to n. When all the terms are 1, then only it is 1, right? In case of so this is and. In case of or, m equals to 1. If at least 1 is 1, then the output is 1. Okay, so it turned out that it can handle, it can mimic all m of n functions, perceptron. But the problem in perceptron is that, as I mentioned, it is not able to separate out points which are not linearly separable. For example, XOR. Okay, let's look at the truth table: 0 0 0 0 1 1 1 0 1 1 1 0, right? So 0 0 minus 1, right? 0 1 plus 1 1 0 plus 1 1 1 minus 1. So these points are not linearly separable, right? Within using one line you can't separate. So as I mentioned initially, that during that time when perceptron was proposed, this example was given, that look, a simple XOR function cannot be mimicked by perceptron. Otherwise, all the basic functions like and, or, NAND, NOR, all these functions can be mimicked, can be modeled using perceptron. Okay, so is it clear, perceptron? Any doubt?
Sir, this problem can be solved by taking an extra dimension.
Okay, that's a good point. How do you do that?
Sir, I think we took an AND of the first two results.
You take the
Sir, AND of the first two results.
first two matlab?
Sir, 0 0 AND will be 0, and then will be 0 0, then 1.
No, I didn't get you.
Sir, we take the AND of the inputs as the third feature.
Okay, you take the AND of the inputs as the third feature. So
Yes, sir.
so you mean so say this is the third feature. So 0 0 0 and 1, and then
So then I feed it into the neural network with weights W1, W2, W3.
with we using perceptron.
Yes, sir.
It would say, okay.
But I think it was AND or in some case it was linearly separable in the third dimension.
It can be. I mean, it can be, but I mean, we are not interested in increasing dimension, but it can be. Do you want me to look at it? So 3D space, difficult to look at, but still let's try. 0 0 0 minus 0 0 0 1, so x, say x y z, x y z, 0 0 0 0 0 1, okay, plus 0 1 0 0 1 0 plus 1 1 1 1 1 1 1 1 1 one probably would come here, right? This kind of space in the 3D plane. And this is minus. Just a minute. This part minus.
Sir,
Wait a minute. Wait. Plus. I don't think. Yeah, go on.
Sir, since we are kind of transforming the previous two features into a third one, won't the previous two features become redundant? I mean, not necessary.
No, these are useless questions. These are not relevant questions. I'm just talking about normal perceptron. Normal perceptron doesn't combine any feature. So let me first understand what he has just mentioned. If you do and intuitively doesn't look like a linearly separable one, but I need to check. I mean, it can be easily coded and checked, right? I mean, you can also code it. You can AND it or it at he suggested, okay, and check if they are linearly separable or not.
So we can use an x equal to y line to separate them in 3D.
With and?
So not with and, but putting them on the line x equal to y. I mean, if putting them on the line x equal to y gives 0, then in 3D we give them a point, say we give them a value 1. Otherwise we give them 0. So in 3D they become separable. -1 becomes separable from +1 +1.
Anyway, so 3D I won't be able to will respond because I don't have I don't know how to visualize 3D plane and answer respond. I mean, it's difficult for me. So anyways, it can happen. You would need to check. It is simple code. You can check and see if it can be done. Anyway, so that's not the main concern. The main concern is that, so this was the perceptron that was proposed earlier, and without any feature, feature combination or whatever, dimension reduction, increase of dimension, if you use this one, it won't be able to separate cases for, say, XOR or XNOR. So now the question is, how do we get these weights? Okay, and we have already seen this in case of logistic regression, but still, let me briefly tell you. So there are two ways, right? One way is called simple perceptron training rule. Okay, perceptron training rule. Okay, what you do in that case, you for each weight, okay, you basically update that weight with some delta change, right? You initialize weights by arbitrary values or possibly equal values, and then you change with this one, with this small values, and we quantify wi delta wi as, some sort of learning rate. We already discussed this thing. It's called learning rate. Okay, and t minus o xi. What is t? T is the ground truth or target value, target function, target output, and o is the output that you obtained from the perceptron. So output of the model, right? And this is multiplied by the feature for which whose weight you want to modify. So this is different from gradient descent and other things that we discussed. Okay, this is a normal perceptron training rule. The good part about this, this simple method is that these kind of methods are useful when, again, data points are linearly separable. Okay, so what is the guarantee that this update rule converts towards successful weight values? So, I mean, you can intuitively think of that this rule converges converges towards successful weight value. Okay, how? For example, say let's say you have some xi which is greater than 0. Okay, and assume that your perceptron, your O, is -1, t is +1 means you need to increase your O value. Okay, because your O value is -1 means your output, the summation that you obtained was negative or 0, right? So it means that you need to increase your weight because xi is fixed, so you need to increase your weight, right? So so if you increase weights, wi, right? Of course, xi wi possibly could come close to t, right? So if you look at the training rule, t minus o, right? So t is +1 and o is -1, so -1 +1, right? With xi. So therefore, so and this is your w, this is your delta w. So delta w is now positive to xi, positive. So therefore, when you add delta w with w1 with original w, the value will increase. So the weight will increase. Okay, in that case, when you have some mistakes. Now think about other case when o equals to -1 or -1 and t equals to -1, or o equals to +1, t equals to +1. Correct case, right? In that case, wi delta wi would be 0. There will be no update. That is also intuitive. Think about other case when what the other cases, when o equals to 1 and t equals to -1, it means you need to decrease the weight. Okay, in that case, what would happen? In that case, you have t minus o, which would be -2, right? And you add a negative value to the weight, so weight will automatically decrease. So intuitively, it seems that weight will eventually converge, and there is also theory which theoretically proved that it would converge to the successful weight that is required. But the problem in this case, in normal perceptron training rule, is this kind of training rule. This is ad hoc, right? And the problem is that, as I mentioned, this is not useful when you provide when you have provided the training examples which are not linearly separable. Okay, because in that case you will have a very different output which may not be expected. So in that case, what we usually do is that we usually follow our usual process, which is a gradient descent, right? Gradient descent based method, right? There, what you do, we have already seen. So our output is ox. We have already seen this is essentially, w time x, right? And here we are not taking the sign. Okay, so our output is not just a minute. So what I wrote earlier is output of sign, right? So while calculating the error, we are not using the sign, we are just taking the absolute value. Okay, and how do we calculate the error? We calculate the error E is mean square error, right? For all data points t, td minus od square. For each of the data points d, this is the ground truth value. This would be +1, -1, whatever, and this is the wi times xi value, right? And we take the square, the usual square root, root mean square types. The reason is that in gradient descent we take the derivative, right? We take the derivative of the error, and this is essentially the derivative of the individual derivative with respect to the individual weights, right? dw1 dot 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 d delta e delta w. Okay, and the weight update rule is same. So we have w, which would be updated by the old one plus the new one, right? And now the new one is calculated by this delta, which is nothing but the learning rate times the, so for example, for I, this is I. Okay, and right, what else? What else? And right, and this is minus n de. I'm assuming that you understand this part because we have thoroughly discussed this in regression. Okay, so and how do we compute this one? Right, this one also we discussed earlier. Delta E delta Wi. This is essentially delta Wi. What is E? E is half sum of all D in D, right? TD we have already written this one now. TD minus OD square. Okay, and usual derivative half times, so 2 and 2 will cancel out, so we'll have TD minus OD, right? And then there's a summation term, then delta Wi TD, and what is OD? OD is this one, right? So OD is W times vector. Remember, these are vectors. Okay, so TD minus OD, and we take the derivative with respect to Wi. So all the other W's will be cancelled out. Only the part which will remain here would be XIT, the ith feature. Okay, dth data, ith feature. So this is and minus, still be a minus always. So this is your delta E delta Wi. Okay, and you'd multiply this with the learning rate, and this is going to be your delta Wi. Okay, and you update it accordingly. So and we have also seen that two types of gradient descent algorithms, stochastic and batch, right? Batch gradient descent, you calculate the error considering all the training examples, then you update the weight. In case of stochastic gradient descent, you update the weight upon encountering a single training sample, right, one by one. Therefore, we also know that the problems, I mean, the advantages and disadvantages of stochastic and batch gradient descent. Okay. This kind of update rule is called this is called delta rule, right? Or it is also called LMS, least mean square rule. These are names basically. Or Woodruff rule. Remember these names, they are same. Okay, so Bolo, any query here? This part we have already covered, so I'm kind of rushing here. Any query here? So this is perceptron. Now coming to a slightly advanced version of perceptron, which is called multi-layer perceptron. Okay. Multi-layer perceptron, MLP. This is a very well-known and standard classifier people use these days. So the difference between multi-layer perceptron and normal perceptron is that here we use multiple neurons. Okay, in case of perceptron we use only one neuron, right? There was only one circle. Now you see that there can be multiple circles. Okay, so say assume that you have 3 inputs, x1, x2, x3, and you have one layer. So this layer is called hidden layer. Okay, it's called hidden layer. Okay, and in case of say in this structure, assume that this is a 2-layer architecture. So this is hidden layer 1, this is hidden layer 2, right? And what are these bubbles? What are these dots? They are all neurons. Okay, so each of these dots is basically same as, you know, this dot, but here we use a different activation function. Okay, so in case of perceptron we use this kind of function, right? But here we'll use a different kind of function. We call them activation function. We'll discuss them separately. So these are neurons. So this is 2-layer perceptron, and you have say so 3 outputs, for example. Okay, 3 outputs, and this is a complete fully connected network. So all inputs are connected to all neurons to the immediate layer, right? So all of them are connected to all of them in the next layer. Similarly here, all of them are connected to all of them. Right? Oh, just a minute. So this would be another. This is okay, and there also all of them are connected to all the output. Right? So this is input layer. This is hidden layer 1, hidden layer 2, and this is output layer. Okay, so all these units in the hidden layers, they are basically standard neurons. Okay, so how do we write it? And why multi-layer perceptron is used? Because it seems that it turned out that since we have multiple, I mean, we'll discuss, we have we use different activation functions, and the activation functions are non-linear. Therefore this kind of representation, network representation, helps differentiate, helps and draw the boundaries in case of non-linear separation. Okay, so let's look at each of these cells, each of these neurons, how it looks like. So here also, same as perceptron, you have inputs, right? X1, X2, dot 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 xn, right? And you have a bias, okay? W0, W1, W2, dot 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 Wn, and X0, which is 1, right? So here also you take a summation first, Xi, Wi, right? And then this summation, so this is till this part, this is linear, right? And then here this additional activation function is used, which makes the linear value, whatever value you obtained, as a non-linear, through a non-linear function. And we call this as an activation function, activation function. There are multiple activation functions that people generally use, but the standard one is sigmoid, right? And what it does, it squeezes the value into 0 to 1, right? So so it is, so whatever you got after the first part is called net value, because it's just a summation, right? And this net value is passed to us through a sigmoid, okay, and the output is O, okay. And we already know what is a sigmoid, which is a sigmoid function 1 by 1 plus e to the power minus net. Yeah, just a standard sigmoid function. It squeezes everything between 0 and 1. Okay, and then it returns what? It returns a probability. Okay, it will return a value between 0 and 1, right? So what is happening here, that you give input, the input can be any real values, right? You give input and these inputs are squeezed, and the output would be a value between 0 and 1, and then again multiple such 0 1 multiple such values which range between 0 to 1 are fed further to another neuron, and then it would pass, I mean, then again some activation functions would be used, and then this output would be passed to another I mean to the output. So each of these layers, as you see, associated with the bias term, right? So this is a bias. Generally, when we draw a neural network, we do not use this bias, and you understand that each of these bias terms, they have these associated weights, and these weights are different, and we also need to set these weights. Okay, sometimes also we have weights, we have bias with the output as well. Okay. So any doubt here in the multi-layer perceptron? You have multiple layers, okay, and when we call this, so this is basically a deep learning, deep neural network. When you call a network a deep neural network, when you have generally more than one hidden layer. Okay, so this is also called as fully connected layer. Now you may ask that why all the nodes are connected to all its immediate nodes. You can also think of not connecting everyone to others, right? We'll discuss later that you can also drop some of the connections if you want. There's something called dropout. Okay, we'll discuss all these things in slightly advanced version. This is also called feed forward network. Why it is feed forward network? Because there is no backward connection as such, so the inputs are basically moving towards up or whatever, from left to right or bottom to top, right? So therefore it is called feed forward network. And so these are fully connected layers. I've already discussed, I've already written. This is also called affine layers, fully connected layers or affine layers. Okay. So now let's, yeah.
So in the last layer we have 3 neuron, right? So the 3 probability functions.
Yes.
Then how to select, like, which one is
the one for which the probability is highest?
Okay.
So it's basically a 3-class classification problem. You have 3 probabilities for 3 classes.
Okay.
Yeah, these are classes. Okay. Anything else? Any other query? All right. So now let's try to write it in a more mathematical way. Okay. So we have input X, right? Assume that this input belongs to a real number of dimension D in. Okay, I'm writing it very slowly so that you understand. We have, and for the time being, you assume that there is only one hidden layer. Okay, there is only one hidden layer. So what this hidden layer does, this hidden layer maps, right, something, maps the input to a different dimension. Okay, and think about this. This is D in. Okay, this is 1 cross 3. And what would be the dimension of this W in this case? The figure that I've drawn, 3 cross 4, right? So essentially it maps a 3 size vector to a 4 size vector. So W is a dimension of dimension D in times D say D whatever. Dx, not x, d int, something like this. Okay, so you have this one and you have hidden layers. Okay, and then you have output. Okay, so this is W1. Okay, so we call this one as W1. This is a matrix. Okay, similarly we have W2. What it does, W2 is of dimension R D int times D out, right? And what is out? Out is the output dimension. Okay, right? And then you have a bias vector of size R. So say bias B1 corresponding to this one. So then D int, and you have another bias B2 here whose dimension is R out. Okay, so how do we write? So look at it carefully. So basically what we are doing, we are multiplying a lot of matrices, right? So we have a matrix X, which is the input matrix, X, which is the input matrix. You multiply this with W1 first, right? Then you add this bias term, then B1, right? And then what you are doing in this hidden layer? You are passing it through a non-linearity, some sort of activation function. Say assume that, so the activation function is sigmoid, I've already mentioned, but assume that it can be any general activation function G. Okay, so you're passing it through a G, or I would say G1, because the activation function for this one would be different from the activation function in this one here, right? So this would be say G1 and this is G2. So this is the output that you obtain from this after this hidden layer, right? Then what you do, you multiply this with W2. Okay, then you add bias B2, right? You multiply this as W2 bias B2, and then you have G2, another activation layer, another activation function which is applied on the output layer, right? So this is the final output, which we call as neural networks in an multi-layer perceptron MLP X. Is this clear? Bolo.
Sir, can you please tell what is D int?
D int is the dimension of the hidden layer. How many neurons are there in the hidden layer? So you have D out, D in number of, yeah, you have D in number of inputs, you have D int number of hidden neurons in the hidden layer, and you have D out number of outputs.
Sir, in a hidden layer, do all activation functions need to be of the same type? Like, will all
Yes,
functions be
yes,
similar?
yes.
Okay.
In each hidden layer, the activation function should be of same type. In two different layers, the activation function can be of different types. But in each hidden layer, the activation function would be same. Otherwise, it would be very complicated, because I mean, after all, you need to take the take derivative, back propagation, to forward pass, backward pass, and derivative would be extremely complicated. Bolo, you have any query?
So within a single hidden layer, we have multiple weights, and for the layer itself, we have one weight.
Within a single hidden layer,
Do we have multiple weights because we have 5 here, for example?
and then
And we have a weight for the layer itself. So
no. So these are your I'm just zooming this part. Okay, these are your hidden this is your hidden layer, and these are your inputs. These are your neurons. Okay, H1, H2 dot whatever, right? And each of these neurons in the hidden layer are receiving inputs, right, and producing outputs. Okay, and you have weights like W1, 1, W, because these are associated with I mean, these are coming from inputs, right? So say input x1, x2, x3, x4. So W11, W21, W31, W41, and then you are generating outputs, and these outputs are moving to different output I mean, moving towards the next layer, right? So you generate an output, right? This output will be multiplied with certain weights, and this weight would be, say, in so you'll have again, say, some w whatever, w, say, 31, w32, w33, 33, and so on. So this is right. You understand what I'm saying? Similarly, like this, weights, some activation, generate an output value, right? You pass the output value to the next layer by multiplying that value with the weights, right? So here you have two weight matrices. One is this one, other is this one. Okay, I call that the first one W1, and I call the second one W2. Right? Dimension of the first one is D1 is D in, because you have D in number of inputs, and how many number of hidden layers? How many number of how many neurons in the hidden layer? D int, int, right? And dimension of W2 is D int times D out, because there are D out number of outputs. Is this clear?
Yes, sir. Got it.
Within a neuron, there is no weight as such. So each neuron, remember two things. Each neuron is doing two operations. One is sum. It is taking the sum of all the inputs. Of course, inputs are multiplied. Original inputs are multiplied by the weights. Sum, and followed by the nonlinearity, which is the activation function. Okay. Then it generates a real value. The real value is passed to the next layer.
So if you take all the neurons, will have like same function, no parameters will change.
So no, same function.
Okay.
Say for example, activation functions are all same, but inputs are different.
Right.
Inputs
Based
are
on
different,
weight, it will
right?
change.
Because
Right.
weights are different.
Yes, yes.
So you see how many weights are needed here. That's the reason we need a lot of data to train, for example, a 3-layered perceptron.
Hello, sir.
Because yes.
Sir, is there any hyperparameter that how many neurons will be used in the hidden layer?
Yes. Number of neurons is the hyperparameter. Number of hidden layers is also a hyperparameter.
Okay.
These are hyperparameters. Okay, so let me proceed. Any question, guys, so far?
So will the model will have some impact by increasing the hidden layer? I mean, whether it will overfit
Of
or
course,
something like that.
of course. When you add hidden layers, it would encourage you to come up with more nonlinear boundaries. At the same time, if you have small amount of data, if you increase hidden layers, it would overfit. Okay, so that is the reason I'm saying the more you increase the layers, the more you need data to come out of this overfitting problem.
Okay, sir.
Okay, so let me discuss now the types of activation functions that we generally use. Okay, we have already seen something called sigmoid function. Let us look at the other types of activation functions that we generally use in deep learning. Although I mean these days people are proposing many new things, but these are very standard, the one that I'm discussing now. So one is the first one is sigmoid, right? Sigmoid function, we'll all know how it looks like. So minus x and oops. Let me draw it in a same scale so that it can also be compared. This is one. Okay, so it squeezes between 0 and 1. So the other one is the other one is called tangent or hyperbolic tangent. The problem in sigmoid function is that it never returns a negative value. In some cases, you possibly need to return negative values. So it is tan h x e to the power 2x minus 1 e to the power 2x plus 1. Okay, and if I draw this in the same plane, it would look like this. Okay, this is minus 1. Okay, symmetric, both of them are symmetric but at different position. So tangent people also use in some cases. There is something called hard tangent. Okay, this is harder version of tangent. So hard tangent x is minus 1 if x less than minus 1, 1 if x greater than 1, or x otherwise. What does it mean? What does it mean? So if now say this is again the same scale, say this part is 1 and this is minus 1, right? So it would look like this. Straight line here, straight line here, and then between minus 1 to 1, the exact x value. So like this. You see the difference between these two? So the difference is here, right? The other activation function that we generally use is called rectified linear unit or ReLU. Okay, this is also very simple. So ReLU of x, you understand what is this x? X is the sum, okay, sum of xi double y is max 0 comma x, okay, which is 0 if x less than 0, otherwise x. What does it mean? It means it basically trims down all the values which is negative, okay, same, I mean, and otherwise if the value is positive, then the same value. So wait a minute. I was wrong in case of hard 10H. I said that the differences are at this two parts, but there is also difference in here, right? In the intermediate part, because I mean, in between -1 to 1, this is a straight line, linear, right? But 10H may not be linear, right? It would be a linear line, exact line. Okay, because the value would be same, x, y equals to x. Okay, so ReLU also, it would be, so when so this is x and this is y. So when x is negative, this is 0. When x is positive, then this is x. Okay. Now, how do we know which one to choose? This is again kind of hyperparameter, but if you look at the derivation, right? For example, for sigmoid function, df for sigmoid, df dx, if you plot df dx, x versus df dx, it would look like this. This is the curve of the derivative of sigmoid function. Okay, the curve of the derivative of tan h df dx would be something like this. Why this derivative curve is important? Because ultimately when we do back propagation, we need to take the derivative, right? For hard tan h, it would look like this. Hard tan h. This is 0. This is 0. Okay, and for ReLU, you also understand, right? How it look like for ReLU? बोलो ReLU के लिए क्या होगा? ReLU derivative, how it would look like?
Sir, initially 0 and after 0 it will be 1.
Yes. Okay. So generally tan h is, I mean, tan h turns out to be better than sigmoid, but when we need probabilistic value at the end, we use sigmoid. But ReLU, being a very simple function, performs very well. There are many cases, for example, in partial speech tagging, ReLU turned out to be very well, very effective. In case of multi-word expression identification, also ReLU turned out to be very effective, and so on. Right. So these are famous activation functions that we use. Now coming to the loss function. Okay, so what was the loss? How did we calculate loss earlier? We calculated loss. We have seen the loss looked like this in case of normal perceptron training. In case of delta rule, our loss was a square root, mean square, kind of a mean square, right? So there are different kind of loss function, because as you understand here, we when we get the values at the output level, we need to calculate the loss, because we already have the ground truth. We take the loss, we measure the loss, and then we back propagate. We'll discuss what do you mean by back propagate. We get the output, we get the loss here at the output cell, and then then we back propagate in order to modify the weights, right? So we'll take a concrete example, and we'll discuss forward pass and backward pass methods in the next day. Let us quickly discuss the some of the other loss functions apart from the square loss that we have seen. Okay, so loss function. Have we discussed the loss functions before? I do not remember. Hinge loss, cross entropy loss. Have we discussed in linear regression?
No, sir.
Regression chapter? No? Okay.
So we have discussed hinge but not cross entropy.
Okay. So hinge loss, binary hinge loss. So +1 -1. Okay. So the intended output y is +1 or -1, and we have got an output y hat from the model. Okay, and since this is binary, we used some sort of sign SGN function on this y hat, and we say y bar, just a symbol. Okay, and the output is y hat or cap. Okay, so again the sign will be +1 or -1. So if y dot y hat, if y dot y hat is greater than 0, what does it mean? It means what? Correct classification? Because if both of them are +1, then both of them are positive, +1, then +1. Both of them are negative, then also +1. So correct, otherwise wrong classification, right? So the loss would be max 0, 1 minus y dot y cap. Right? So if it is correct, then we have +1, then the loss would be 0. If it is incorrect, then it would be what? Then it would be -1, right? And then the loss would be 1 + 1, 2. Okay. So the same concept can be extended for multi-class hinge multi-class. Okay, multi-class. Let us assume that you have this y, which is now a vector. Okay, y is a vector multi-class. So kind of one hot. So one would be 1. So assume that this is 3 class. Okay, it's a three class classification problem. So y would be a vector. This is ground truth, right? For each class, one say the class is black, green, and blue, black, green, and red. So one would be 1, other would be 0. Okay, one hot kind of. Why this is called one hot? Because this is a vector with only one entry as 1. Other all the other entries are 0. It's called one hot. Okay. So these are all modern names. Nobody used these terms 10 years before. You have output y cap. Okay. Similarly, you have again 3 classes, for example. Okay. Y cap 1, y cap 2, y cap 3. Okay, so your actual prediction, and you have certain probability values here. Okay, certain values, say 1 by 6, right? Some values here, 2 by 6, 4 by 6, and 0. So what would be your prediction? Predicted class would be what? Argmax y hat I, right? In this case, it would be 2 plus 2, right? Because for class 2, this is 4 by 6. So this is your prediction. And similarly, you have correct class, say T, which is again argmax I yi, right? Which in this case again 2, because this is 1. Okay, so loss would be max 0, 1 minus y, and let's name it. Let's call this yi, not yi. Say this is k. Okay, the class k. So yi not, sorry, so just a minute, yk cap, and this is t, right? So yt. So basically you are taking the value for which the number is maximum. So in this case, this would be what? This yt would be 1, and yk hat would be 4 by 6, right? This is the loss. Okay, now remember one thing here, t and k may be different. Okay, so coming to the next one, which is binary cross entropy. We already know what is cross entropy, right? There are two distributions, say for example x and y, right? Let's think of two discrete distribution, x1 x2 dot 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 xn, and y1 y2 dot 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 yn, right? Normal entropy for x, xi log xi, for y minus, of course, minus yi log yi. In case of cross entropy, this would be minus xi log of yi. Okay, so here also the same thing applies. X, in our case, we have y and y cap. Okay, y and y cap. In case of binary cross entropy, so you have only two values. One is, so y cap, only two values. One is y, other is 1 minus y, right? So it would be what? It would be binary cross entropy. So y, so minus y log of y cap minus 1 minus y, because there are only two values. One is y, other is 1 minus y. 1 minus y, right? In this set, where in the first case we see that there are n different cases, in different values. You have only two values here. One is y, other is 1 minus y. Similarly, you have y hat, 1 minus y hat. So y log of y hat minus 1 minus y log of 1 minus y hat. This is called binary cross entropy. Okay, it can be extended for categorical cross entropy, right? For multi-class categorical cross entropy. where you have multiple classes. So now your y is a vector. Okay, your y is a vector which is y1, y2 dot 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 yn, and y cap 1, y cap 2 dot 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 y cap n. So loss would be minus sum of yi log of y cap I. Okay, so if you look at binary cross entropy, you see that if say y, if so, there are 4 possibilities, right? Y cap, right? Binary. So and remember, y is binary, 0 or 1, but y hat is the prediction. It can be, it is basically a probability value, right? So it would be right, it would be there are 4 cases. One is 0, and the y cap is 10, y cap tends to be 0. You have 0 and y cap tends to be 1. You have 1, y cap tends to be 0, and you have 1, y cap tends to be 1. So these 2 cases are correct cases. Loss should be 0. Let's look at here. So when y is 0, when y is 0, right, this part is ignored, and in that case this would be log of very high value tends to be 1. So this part would also be 0. So the value would be 0 overall, right? When 1 1, then 1 minus y, this would be 0, this would be 0, and this part would also be tend to be 0 because log of 1 is there, right? Now when 0 1, so 0 1 means y is 0, so 1 minus y, this would be 1, and you have this value, right? And of course it tends to be 1, so this 1 minus, this is not 1 minus 1, right? This is say 1 minus 0.98. Okay, of course it may be possible that you have log of 0, right, in some cases. So you just assume very small values and you skip the log 0 part, which is undefined part. Okay, otherwise you see that when you have when y is 0, this component will be considered. When y is 1, this component will be considered. Okay, you see the difference? You see the do you understand like how it works? When y equals to 0, right, when y equals to 0, this part will not be considered, only this part will be considered. When y equals to 1, only this part will be considered, this would not be considered. Now depending upon the values of this log, because y is just 1 or 0, right, depending upon the values of this log, the penalty will increase or decrease. Okay, so this is cross entropy, binary entropy, cross entropy, and we already have seen the square loss, right? So these are some of the loss functions that we use. Okay, how many of you are awake? 106.
Excuse me, sir.
Yeah.
Sir, am I audible?
Yes, yes.
Sir, can you please scroll up in second point?
Yeah.
Sir, when we will get the 0, when we are writing L is equal to maximum of 0 comma this, because I was saying that 1 minus of something, and we will get the maximum 0 as when the second term will be less than 0, means negative.
When the second term is I mean when this term is, when the whole term is negative.
Yes, sir. In what case it will be negative? Because
think about it. Very good question. Think about it. So when this would be negative, this would be the entire part would be negative. When yt minus y, this part is negative.
Yes, sir.
Right. When this part would be negative.
So for this part to be negative, yk has to be like, we will get yt always 1, right? Like yt will be always 1 because we are doing one hot encoding, so we'll get. Like, I'm not able to understand this part.
Anybody wants to respond? Remember, this is a generic loss function. This is not only applicable for this case, one hot. This is a generic loss function.
Okay.
In some cases, it may be possible that your output is negative. It's a generic loss function. I explained this formula using probabilities 1 and 0s and so on.
Yes, sir. Yes, sir.
Any other query? So this was a simple introduction of basic neural network, perceptron and all. Next day, what we'll discuss, we'll take an example, a real example, right, with some numbers, random numbers assigned to weights, and we'll derive the forward pass and backward pass, forward propagation and backward propagation procedures, okay, with some example. It would take a whole class. That's the reason I did not want to discuss this one today. Okay, and when we use this loss, sometimes we also add some regularizer, right? Some sort of regularizer can be L1 or L2 regularizer or something else, right? Just to even avoid the overfitting cases, make it more generic. Okay, so loss, some sort of loss with parameters, say L1 loss W plus lambda 2 regularizer. This is overall loss function that you want to minimize, argmax, argmin, theta, or W, sorry. Okay, so let me stop here today. Next day we'll discuss forward and backward pass algorithms. I can take a few queries if there is any. Anyways, thanks.
Hello.
Yes.
So can you move to the second loss function, the multiple, multi-class range function. So can we also not take the loss function as the summation of the summation of the error between the target and the predicted part, like for one hot encoding, if we get suppose if we are getting 0 1 0 and in output we are getting 0.5 0.2 0.7,
but that's not the hinge loss. That is not hinge loss. I understand what I'm saying. You are saying that 2 by 6 minus 0 plus 4 by 6 minus 1, whatever, plus, but that's not hinge loss.
Okay, sir.
That is again one kind of loss. Yes.
Sir, in general, when we tackled the hinge loss, we saw that we introduced the 0 because we were getting the negative terms. But sir, like here we are not getting the negative terms, but we will write it in a proper hinge loss.
Yes.
This is what we want
to
consider.
Yes.
Okay, sir.
Okay. Cool. So some of the parts I have followed from the Tom Mitchell part, and some of the part was my earlier notes. So that one I do not have anything. I mean any standard notebook as such. But all this hinge and ReLU, all these things are already. There are many such materials available online. So you should be able to get them online. Okay. Okay, chalo. Thanks. Bye.